take a couple of minutes to promote my institute because it's very much associated with or related to this type of work in remote communities, not only in Canada but across the world. Some of the slides I'm going to be discussing here come from students of mine or former researchers of mine that have generated all this most of this work. So, and I wanted to acknowledge that, and since Intrajit Das is attending, you will see some of his work presented as we move forward. Please, next slide. Next slide, please. No. Thank you. Okay, so I just want briefly to introduce WISE, which is Waterloo Institute for Sustainable Energy, which is focused on clean and accessible energy and affordable energy for all. So that's one of our main vision. And in that context, we collaborate within the University of Waterloo and outside. We reach out to the collaborations outside the university, and we also look for having some influence in all the debates related to energy systems within Ontario and outside Ontario as much as possible. And it's part of the reason why I'm here. Next slide, please. The Institute is really formed by members, faculty members, and their students and researchers, and they lead multiple labs, all dedicated, in this case, 30 labs dedicated to research, and we are in the process, hopefully, to acquire a microgrid one. We have a professional team that basically what it tries to make sure is that supports and establishes links between not only faculty members, but within Waterloo, but outside Waterloo, and industry in particular. And we have this global look because we have a lot of collaborations, particularly with Karlsruhe Institute of Technology, which is one of the initiatives I'm going to describe in a second. Is very much involved in our collaborations. And we are embedded with this culture of innovation, which is Waterloo, which is an incubator of multiple, especially IT companies, because of RP policies. We generate quite a bit of startups within the context of Ontario and Canada. And next slide, please. So as I said, we're involving multiple facets or aspects of energy research, from generation to transmission to distribution, usage, and of multiple energy vectors. Electricity is certainly one of them, and it's becoming much more relevant in the context of net zero and electrification for the decarbonization of our energy systems. That's the backbone of it. But however, we do a lot of work at different levels. Our faculty members work at different levels, or members in terms of materials, in terms of equipment, in terms of systems, and in terms of policy. Next slide, please. We are very much embedded in the SDGs, and we particularly contribute to the SDG 7, which is affordable and clean energy, as you'll see in our next slide. But we also somewhat contribute to other SDGs related to the issues of health, climate change, environment, etc. Next slide, please. I'm trying to keep this short, so if you have any questions, I will be happy to address them later. One of our main initiatives, Affordable Energy for Humanity, which is very much related to SDG 7 and related to the motivation of this particular workshop. And these are our partners. What you see here is a picture of our partners across the world, in which we have collaborated, or are working with, or have worked with. Next slide, please. This initiative. Next slide. This initiative was set up by Professor Natwani, the former and founding member of WISE, and also, as I mentioned, Professor Neville at KIT. And it was a collaboration built around providing solutions for SDG 7. So we have 157 members from all over the world. 37 is very, very evenly distributed. We have academics, private and non-profit government organizations involved, mostly from Sub-Saharan Africa and South Asia. And most of our projects focus on student work, integrated learning, collaborative projects, many of them, and set up of multiple events, all within the context of affordable energy throughout the world. Next slide, please. In fact, we are now involved in a major funding requests to support this work to move this forward. This work. This is the team, and we used to have another member, which unfortunately left, which was in charge of this particular initiative, which we hope to replace soon. Thank you. Next slide. So getting down to the topic at hand, these are the partners that have been involved in this research. NRCan, which some of our participants I can see are involved in this call, in this event, which we're very appreciative of. We have an MOU, we must have an MOU with NRCan to work in some of these aspects. Hatch as well, WWF funded our interactions with the Canadian North, particularly the Arctic, and Hydro One with Northern Ontario. And we work very closely with that community at some point. Casablanca Lake First Nation, which I'm going to be mentioning, and Canadian Solar as well was involved in all of this research. And we are now in the process of trying to transfer the facilities, the microgrid facilities they develop for remote communities to be a part of our lab inventory within WISE. We also work with Innovus Power, which I'll mention soon. And we are now involved in a new initiative funded by NSERC, ITEM, hybrid thermoelectrical microgrids, in which I present some of the results, and the energy model initiative related to funded by NRCan as well, by the way, related to hydrogen research, in which we are now involved again. Next slide. Now, some of what I'm going to be focusing on is giving you an overview of Canadian remote communities. Although it might be a bit dated now, because although the landscape has not completely changed, it still is diesel-based microgrids throughout the north. And although that's changing, more renewables are introduced. In some communities, actually are reaching 20% of the generation level. So things are changing. Hopefully, I like to think that we had something to contribute to that particular change. I'm going to be describing the planning framework that we develop, in which some of this work is, some of our contributions are based, and the applications to one community and 2 regions in the Canadian Arctic, relevant to this particular event. And now more recent work in hydrogen energy storage systems, which is being sort of expanded to include ammonia in our collaboration with, in which Alaska is involved as well, through EARNEST, a project being funded by the Department of Energy. I'll talk about district heating as well and provide some concluding remarks. Next slide, please. Now, next slide, please. Thank you. Yeah, one slide less, please. Okay, so I'm going to be providing some references in case you want to dig into all these details. Our first contribution, which goes about a decade ago, we've been involved in the research for over a decade. It refers to what the situation in the Canadian North is, and basically is focused on describing what the resources are and what the microgrids of electrical systems in the North are, which are mostly based on this. And this is not only relevant to Canada, but also India and Chile. In Chile, in particular, we work with Chilean colleagues as well, in which they have a similar situation. And the dominant source of energy is diesel generation, as most of you know, which has been changing slowly but surely. And some of these communities have access challenges, in terms that they can only be accessed through winter roads, which are now becoming a problem as well. The loading of some of these frozen rivers have decreased by half. So that's creating a major challenge in terms of distribution of provision of diesel generation, for example, or diesel fuel, pardon me, for generation. So because many of these have no remote no road access. Now, the major challenge and the major interest in all of our work has been how to provide reliable renewable electricity to these communities, which is now slightly happening with significant funding from, at least in Canada, from the federal government and provincial and local regional governments. Now, the intention is not only to clean these systems in terms of environmental emissions and issues of spillage, but also the issue of reducing costs, because it's a very costly enterprise in terms of generation based on this. Next slide, please. We got to keep in mind that these communities, which I show here, this is an inventory we did, one of the first inventories available in terms of remote communities using GIS tools as well. That I noticed they were mentioned. And gives you a picture of what the remote communities are in throughout Canada. So as you can see, they're very much spread, and many of them are in the Arctic region, and vary in size from very small, you know, hundreds of kilowatts to megawatts. Most of these are diesel based and far away from electrical grid. It's interesting to see that, as you can see in Northern Ontario, that is changing dramatically, because most of those communities that you see in the Northern Ontario region are going to be hooked up to a 230 kV line that is being built by the government, which was talked about for decades and now it's been built. And all of these communities are going to get off diesel and connect to the main grid. So that is changing. So as I said, this is changing significantly. And many of these communities now have, in the Arctic, for example, have access to wind and solar. For example, Inuvik has reached 20% of wind and solar contribution to the microgrid, to their microgrid, to energy systems. Next slide, please. So we got to realize that there are very significant wind resources. And especially in the areas close to, as you can see in the north, in the Arctic, close to the sea, close to the ocean, and that's a very important resource. Next slide, please. However, PV also plays a role. As you notice here, the southern parts of Canada have not really insignificant amounts of solar resources, and some of these communities are actually taking advantage of that. However, in the north as well, they have been quite significant deployments of PV with new technologies, new angles, new deployments, and they are playing a role in the cleanup of the electrical systems in these communities. Next slide, please. This is what is actually happening now. Okay? As opposed to what in theory, what it looked like a decade ago. Now, the work we have been involved in is optimal planning. So how to determine the optimal resources, the equipment, the sizes, the cost, and also considering social and community issues, which are a significant concern when you are dealing with these communities. As our colleagues in Alaska know well, you need to establish relationships within communities and keep them very much involved in implement all these changes or try to implement these changes. Otherwise, and the whole work ends up being just a paper, and we basically taking advantage as academics, taking advantage of their needs, which is obviously not a good approach. Next slide, please. So that's why we were involved with very closely, directly with the Casa Monica Lake First Nation community, and through WWF with the regions of Nunavut and Northwest Territories. Now, the feasibility, the idea is to basically look at the work we were doing, look at the feasibility of RE, and in that work, we do an optimization that consider minimizing O&M costs. We would not look at other issues. Yeah, I guess it's going faster than I thought, but basically these two, yeah, go ahead. Next slide. So keeps me moving. These two papers describe that framework that we developed. In which we develop in 4 sections. First, collecting data, then forecast, and then identifying the equipment that would be deployed, and then applying these optimization techniques that is described in these papers to the understanding, basically to the planning problem. Next slide, please. And then we apply these to first at the community of Casa Monica, which is located about 1,500 kilometers north of Toronto, about 500 kilometers north of Thunder Bay. There's no roads. This is a picture of the community and this location. Interestingly enough, all of this is changing. This community is going to be hooked up hopefully soon to this new 230 kV line going across all the north. That is going to also, part of the reason is mining development in these regions. Next slide, please. In which, by the way, this is gone and it's being developed with communities, local communities in the region, because as I said, It's not that one comes and parachutes in the middle of it and tries to do things on its own. This is the community. As you can see, this is the picture. Next slide, please. It's about 1,000 people. As I mentioned, 500 kilometers of Thunder Bay, only winter road access and air. And when we were working with this community, they had 3 generators. And eventually, after we left, 1 generator, which was another major challenge in these communities, availability of energy, electrical energy, was replaced, the smallest ones, with a 1.5 megawatt diesel generator. All of them diesel. However, this community was unique at that point in the sense that had wind turbines. One of them deployed when we were part of this project that we were involved in, and a 10 kilowatt solar PV array. So that was part of the reason motivation to establish links with this community, and they were quite interesting. There was a champion at that point in charge of the energy development of the community, which was very interested in participating on all of these and allowed us these interactions, which were very useful. Next slide, please. So what we did in this project with Hatch and with NRCAN funding, next slide, please, is deploy a whole bunch of measurement equipment to understand. At that point, all of these issues were not really very understood, and we deployed very, as you can see throughout the community, very detailed data loggers in some of these generation stations and loads. Some less fine measurements in terms of some of the measure loads, and data loggers, which we're talking about one in terms of fractions of seconds, another ones in seconds, another one in minutes. In terms of data loggers in some houses across the community. Next slide. And this gave us a picture of what the energy demand, the solar resources, and the wind resources, because we also deploy adequate equipment to measure the resources in this community. Next slide, please. And the results of this application was that it made a lot of sense to deploy wind and solar in this community. Wind was dominant, but solar as well played a role. And it was also determined that the location made a difference. Why? Because some of the community buildings pay different rates that come out from the funding that the federal government and provincial government provides. So that gives us a different picture of the economic feasibility. Next slide, please. Which is basically presented this. The bottom line of this is that for different cases, all of these made economic sense. In the sense that if you look at the long term, you basically not only recover by save money. So the problem, the main issue that we face in all of this and many communities face is CapEx, and initial investment to make this happen, because we're talking about millions of dollars. And then the NRCAN, the Canadian government, and through NRCAN has set up a funding mechanism to significant major funding mechanism to deploy this equipment to try to address this issue, which is now operational and it's active, and some of these communities that are taking advantage of this. Next slide, please. And then we move to the Canadian Arctic. We work with WWF in these communities, Nunavut and Northwest Territories, and the results of that, this is work that was led by Indrajit Das, which is in this scope. Thank you, Indrajit. So if you have any questions, you can ask him directly. And then we worked in these several communities. So we did a pre-feasibility, feasibility study of renewable deployment in these communities. Next slide, please. We interacted a lot with the local utilities, which was very helpful. This is the pre-feasibility study, which allows us to identify in terms of quantifying and qualifying the communities that would be more sort of dominant, to do more detailed studies to determine the feasibility of introducing renewables in these communities. And we identified here basically 18 communities in which we focus on in more detail. Next slide. And then we did a more detailed study of these communities to try to determine what would be the advantages or the benefits for this community in terms of the deploying renewables, not totally eliminating diesel, because that doesn't not yet feasible because of cost, basically. Although in theory one can eliminate totally diesel introducing batteries, but that was very costly. And still is costly. And then we looked at, and we ranked all these communities. And then we did a very detailed study, next slide, please, in which we apply this planning work for some of these communities. For example, Sani Kulak is one we focus on, and the planning study was looking at 20 years and in yearly averages of the resources and the load. Next slide. Temperatures as well. And then this is the result for that community. And basically, the bottom line of this is that it was really made sense to deploy solar, wind, and batteries in these communities, and it was economically feasible, and made sense in the long term. However, as you can see here, some of these, I mean, we're talking about $10 million savings in this community was significant, but you needed a significant investment right off the bat, and that's the major hurdle that had to be or has to be still sort of face when you're doing this type of deployments. Next slide, please. And then this is the detailed study of multiple feasibility. The bottom line of this is the cost. If you look at this, some of these communities are more appropriate than others, but there are significant savings that would easily pay for the initial investment in terms of saving diesel and saving making the cost of electricity cheaper. And then we looked at next slide, please. We looked at another option with a company that was interested in looking at what the variable speed generator, diesel generator, what kind of a difference it would make. The interesting feature of these generators is that you can, instead of going from 40 to 100%, you can actually load this generator all the way down to 10 because of the variable speed, and you can also introduce energy storage of supercapacitors in the middle in the DC link here. So that has some advantages, and then we studied this issue. Next slide, please. And then we noticed that bottom line of this is that in these communities, it did make a difference. So in other words, the best option was to introduce VSG, which in some cases was able to reduce the amount of energy storage and hence cost that required to increase reduce the cost of electricity, as you can see here towards the last 3 columns, and also reduce the need for batteries. So that's the bottom line of this. So next slide, please. And then we looked at, okay, how about hydrogen? And then there are these publications that we have with funding from the electrification, the energy modeling initiative. We developed some studies in this particular community, and developing an optimal planning model that also considered hydrogen in the picture. And if I may, next slide, please. Trying to move forward along. So we apply this to Sunny Crillet based on the data. Previous slide, please. No, this is going too fast now. Previous slide, please. Previous. Thank you. So the bottom line of these results was that hydrogen does make sense. Even though, I mean, costs, I guess, have somewhat reduced, but still is costly. However, the long-term storage capabilities of this, which has already been demonstrated in some communities, particularly in BC, in the community of Bella Coola, that hydrogen does make sense when you talk about long-term storage. And in that sense, that's what we were able to demonstrate in these studies for this community now in the Arctic. And now we are expanding these to include ammonia and doing some studies as part of the EARNEST project funded by DOE. To see what kind of looking for. We're working with establishing links with the community to look at what would be the difference now, more real, more closer to the community, instead of just a study, and hopefully potential deployment of hydrogen and ammonia which is the new idea here in these communities. Next slide, please. And finally, we look at district heating. And this is the work under the umbrella of NSERC High Temp, which is basically looking at combined district heating and electric power networks, and what would be the advantage of that. And the motivation for this is the fact that you still have this in these communities, and they have significant engines exhaust from the engines. That's heat that can be used as a thermal source for the community. So we looked at this study in a lot of detail. And we try to understand the dynamics and not only the static dynamics within Lucas Coast in this case, because there are significant challenges in terms of the community, because extreme cold, soil limitations, heat loss, etc., that have to be considered. We were able to design in very detail the network and then study it in conjunction with EPN, and we noticed that these heat pumps can be very beneficial, not only district heating for providing thermal energy as well, which is very important in these communities, but also for frequency control. Next slide. So we applied for the Casamonica Lake First Nation. Next slide, please. Thank you. And we designed the network in great detail. We look at the electrical power system. We assume that we had, at some point, they were considering deploying 250 kilowatt solar panels. There was a very detailed study, feasibility of that, and was seriously considered. That didn't happen, in part because now there's a grid, a line going through the community. And we looked at this, and just the bottom line is that it was feasible to use with a very careful design of the network, the district heating network, to provide the thermal needs of the community and keep temperatures within the ranges, which is the left-hand part, right-hand picture on this slide. And then we looked at what kind of impacts it has, and we looked at the advantages of having frequency controlling all of this. And that's the next picture you see here. And we compared multiple cases. Basically, we demonstrated that with this interaction, you can actually facilitate renewables. Next slide, final slide, which is the conclusions. So, introduction of renewables, okay, you can have substantial, and this is now a fact. Now this has been proven, and it's actually happening. The deployment of renewables is feasible, and it will significantly reduce emissions in these communities. And not only that, in the long run, it makes economic sense. Now, in this context, if we're going to keep this all around, which I don't, that's something that I don't think in the short term is feasible to get rid of. The deployment of new generation, if is needed, has to be done through probably variable speed generators. Now, even though wind energy is more prevalent in this community, solar is also part of the solution, and it's actually happening right now. It's been demonstrated that does help. The battery deployment is somewhat limited in all of these studies we did, and continues to be limited because of the high cost. And hydrogen as well is an alternative that should be considered in spite of the high cost. But for seasonal storage is really a solution, and that is a good contribution mix between solar and hydrogen. And now, the district heating networks is also another option to be considered. It's a challenging option, but we believe that will help in all of these issues, as long as you have still diesel generation. And in all of these, the studies that we did make a compelling business case for renewables, energy storage, and district heating. District heating, we did not look at the economics, but all the people have looked at that, but it would be interesting to see. And the major issue that has to be addressed, and it's being addressed, is the issue of CapEx to make this happen. That's all I have, hopefully within my 30 minutes. Thank you. And I think questions will come later.
Thank you very much, Claudio. So we'll have questions closer to about 11:30 our time in Alaska. So
okay, I'll stick around.
Okay,
I'll return.
perfect. We'll take 10-minute break. Can we do that? Yeah. So we'll be back in 10 at the latest.
Thank you.
Thank you.